Okay, in this lecture we're going to look at Brownian motion and a little bit of the fluctuation-dissipation theorem and also at the end some financial applications of this kind of process. Brownian motion is absolutely fundamental to stat mech. It's one of the most important things we will do in this course, and it's an example of a random process, and of course in this course we're always doing random processes. Things are often random, very statistical, but just because they're random doesn't mean we can't say anything about them. This whole course is about saying things about random processes in many ways. Okay, so Brownian motion. This was discovered by the Scotsman Robert Brown, looking in a microscope and looking at bits of pollen move about in probably, I suppose, the early 19th century. But it was studied in detail by Jean Perrin, the French physicist, one of the great French physicists, and he won a Nobel Prize for this in 1926, which we will look at in a little bit. So there's Robert Brown on the left. On the right we have Mr. Perrin, who was probably one of the coolest looking physicists there was. Not many physicists have wild curly hair and a big beard and a funny pointy beard. What about Perrin? We're going to look at Perrin first. So Perrin was born into the Belle Epoque, the great period of optimism which followed the Franco-Prussian War in 1870 and finished with the First World War. And this period, in hindsight, was a period of great fun, optimism, beauty, speed, sophistication, style. Automobile, aeroplane were invented. This is when the modern technical world actually starts. This is when the Eiffel Tower is built, for instance. And it's a world where progress seems inevitable and where, at least in Europe, there was a great deal of positive optimism about the world. Okay, great technical processes. This is when the modern world, in some sense, begins for most people. Okay, so when I say most people, I mean ordinary people, working class people, basically people who are working in factories and things and on the land. Okay, so let's look at Perrin's experiment. Okay, so Perrin observed small particles of mastic, which is a plant resin material, of radius quite small, 0.53 micrometers, at 30-second intervals. Okay, so you watch them in the microscope, you watch these things move around, and the grid size here is 3.2 microns, so that's one grid size there. Okay, so he's just watching particles move around in a microscope. He's putting the particles under a microscope in a drop of water and looking at them. And what he notices is the sort of thing which Robert Brown had seen before, which is the particles undergo this kind of weird random walk. Okay, looks like that. Okay, very, very simple experiment. And what Perrin noticed was that he's plotting the particles every 30 seconds. Okay, but if he looks at the particles between those 30 seconds, he sees the same kind of thing, the same kind of random walk, but in miniature. In other words, if you took this bit here and you watch the particles not for 30 seconds, but for 1 second, you would see this kind of thing, except on a smaller scale. Okay, and so it's a self-similar random walk. If you look at it in more detail, you blow things up, you see the same thing again. Okay, and that was noticed by Perrin during his experiments. So this points to the fact that the random walk is a fractal. Okay, so you can measure the path length, i.e. the contour length. The path length here, contour length, okay, which is this sort of thing, right? Here's my thing. The contour length is that length all the way along there, right? Okay, and you can measure that using different step sizes. So here we've tried a step size tau, okay, and if you measure it, what you find is that the actual contour length you get, L, the length of your path, is a function of tau. Okay, it's a function of that, and it goes as tau to the 1 minus d, and for a Brownian walk we can find out that d is equal to 2, so the length is proportional to a on tau, the length of your walk. Okay, so as we make our step size smaller, L increases without limit. Okay, so the length you get, the contour length, depends on the size of your measurement, the size of your ruler in some sense. Until at least we make tau so small that it's of order of the molecular collision time. Okay, in which case this starts to break down. It's no longer a fractal. All fractals have some limit below which you can't probe things anymore. So let's go rogue a bit. Let's go off slide a bit and have a look at why that's the case. So suppose we have a random walk here. Let's do a random walk like this. Okay, it has size r, and our random walk might have n steps. Here it's like 5 or 6 of size tau. Tau is our step size. This is r. It's r there. Now, of course, we know from a random walk idea that for a random walk we have r is roughly equal to, I'll set it equal, but it's only roughly equal to, the step size tau times the square root of the number of steps. Okay, that's what r is. Now, let's suppose we took Perrin's experiment, but we didn't measure the step size tau. We looked at it in more detail, and we had a step size tau prime, which is equal to tau divided by p. So we've made it much smaller. So in other words, I'm going to take this whole random walk here, and I'm going to do the same random walk. I'll take a video of it. So I've got a video. I can look at it more closely, and I will find it looks like this, with many more steps. And arriving back, of course, at the same place. And each of these steps now is of size tau prime, which is tau on p. Okay. Now, I know my random walk must have the same size. Okay. So r prime here, this size, must be equal to my original random walk here. This one and this one must be the same because they're the same random walk. So r prime equals r. Okay. And I also know that r prime, because it's a random walk, must be equal to tau prime times the square root of n prime. That's the definition of what a random walk is. Not definition, but that's a property of the random walk, so we say. Now, so therefore, we can equate these two. We can equate that to that. Okay, and we get tau prime n prime equals tau root n. And that tells us that n prime, the number of steps I've got in my new random walk, is equal to tau on tau prime squared times n, and tau on tau prime is equal to p squared, or tau on tau prime squared is equal to p squared. So that's the number of that's the number of walks, that's the number of steps we have. Okay, it's p squared times n. Okay. Now, what do we want to do next? Well, we want to figure out what the contour length here is. So in our original random walk, the contour length L was equal to n times tau. Okay, just adding up all the different bits, 1, 2, 3, 4, all bits. That's the length of the contour length. The contour length of our new walk, L prime, is equal to n prime t prime, tau prime, the same thing. Okay. And that's going to be equal to, okay, now remember n prime is p squared n, so we've got p squared n here, that's from that equation there, and tau prime is equal to tau on p, okay, so it's equal to p n tau, which is equal to p l. So L prime is equal to p times L. So I've decreased my step size by a factor p, and in doing that, I've increased my contour length by a factor p as well. Okay, so it depends. This is a typical thing to do with fractals. You measure the Australian coastline, for instance. If you measure it on a metre scale, you get some kind of length, but if you measure it on a centimetre scale, you get a much bigger length. Okay, and that's very typical of all fractals. So we just proved this result here, that the length increases without limit. Okay, as you go to smaller and smaller length scales, the contour length increases without limit. Okay, so the first person to analyse this theoretically, actually I wouldn't say the first person, one of the early people to analyse this theoretically was Einstein. The Einstein theory is based on something very, very important in physics, which I tried to emphasize before, which is ignoring the details. So ignore the details. Okay. Don't sweat the small stuff. Okay, so we imagine the Brownian part divided into steps of time length. Here's a time length rather than length, but time length tau. Okay. Each step is the result of smaller steps which we can't even see. Okay, so we're going to have the case of one dimension, and we're going to have some walk x of t. Okay, so just walking like this, like this. Okay. In time tau, we move from x here to x plus delta here. Okay. Where delta is some size which is distributed probabilistically. So sometimes you might move from there to there, and the next step you might move just backwards a little bit. Next step you might move backwards a lot. So there's a probability distribution for this step after each time step. Okay, and that obviously must be between minus infinity and infinity. Okay, so delta is picked from a probability distribution f tau of delta. So delta is the size it moves in time tau. But that delta is not deterministic, it's probabilistic. It can be in a wide range from minus infinity to infinity. Okay, so the probability that delta is between delta prime and delta prime plus delta prime is this. Okay, that's our probability distribution for the step size delta prime. Okay, so what does Einstein assume about this probability distribution? He didn't assume very much. Okay. He assumed it must be symmetric. Okay, it has no biases forward or backwards. So the particles, on average, it's not moving forward or backwards, but it's it's moving all around randomly about the place. So this tells us that fact. F of delta is f minus delta. And he also assumes you can normalize it. That's not completely obvious, but it's an important property you have to have. You can normalize the distribution. Okay. Now, let nxt be the density of particles. So we've got the density of particles, number of particles per unit length in one dimension. So that's the density at position x at time t. Okay, so the number of particles displaced out of the length delta x in time t, tau, is roughly this. So each time tau, you've got some particles in this tiny length here, dx. Okay, and you want to say, right, the number of particles in there is just nxt dx at some particular time. That's the number of particles. That's that bit there, and we want to look at the fraction that are displaced out of it, right? So very roughly, that fraction is the fraction which will move backwards by more than dx, or forwards by more than dx. Very roughly. Okay, so that's the fraction moving backwards. That's the fraction moving forwards. Okay. And as dx approaches zero, what you find is that this sum here is just that. It's the whole integral, of course. Okay, so what am I doing here? No, I don't want that. I want this. So that's the result we get, which of course this is normalized to 1, because we know that from up here. And therefore we get this is the number that leave. Okay. And basically what that says is that all the particles originally in it are kicked out of this region. So in a time dx, in a time dt, time tau, all the particles that are in here are being kicked out. Okay, because dx is infinitesimally small. That means that all the particles that are in this region at time t plus tau must have come from somewhere else. They can't have come from here because they've all been kicked out. Okay, so where they come from outside. So they come from over here and over here, and you can rapidly figure out, if you want to, the distance they must have moved. If they're at x, they must have moved backwards at a certain distance, delta, to get into this region, and that's the distance they must have moved. And this is the problem. This is just counting them all, multiplied by the probability distribution. Okay, so what we have here is the number of particles that are in this region at x of length dx at time t plus tau must have been somewhere else, and the somewhere else they must have been is given by this integral here, and that tells you where they were, what the density was, and how far they moved. Okay, and you can figure that out for yourself, but it's It's fairly straightforward. They must have come from somewhere else, and this tells you how far they've travelled. All right, now we can take this equation back here and do a Taylor series of both sides. Okay, so let's do a Taylor series expansion of both sides. We're going to Taylor expand the left-hand side in terms of powers of tau. So this nxt plus tau is basically just nxt plus tau times d nxt dt evaluated at t. Okay, and so that's that bit there. Okay, the right-hand side we evaluate in terms of powers of delta, and we evaluate this bit. We expand that part. So this says, nx plus delta is equal to nx plus delta dn dx plus delta squared on 2 d squared n, off the page here, d squared n dx squared, which is this bit here. So we've got that bit there, that bit there. Okay. Now, let's look at all these terms. On the right-hand side, we have this bit, okay, but that bit doesn't depend upon delta, so we can take it at the front there if we wanted to, and this normalizes it to 1, that's just 1, so this term and that term cancel out, so we get rid of them, okay. Okay, so that means that term and that term are the same, okay. Now, the second term is 0 because, this term here, right, it's 0 because we can take this out the front of the equation. It doesn't depend upon delta. And we already know that f of delta is an even function, and so the delta there multiplied by that gives us 0. So we're going to get 0 for that. So that term's 0. Let's get rid of it. Okay, and we're left with this term. Okay, and that term here, this one, is now it's very easy because we can take that again out the front here, and that's what we've done just there. So we end up with this equation, which is much, much simpler, and we can then rearrange that equation if we want, divide through by tau, and we end up with something that looks like this. I'm going to take the limit as tau approaches 0 as well, and what we end up with is that equation where the constant d is given by that. And so Einstein has managed to derive the diffusion equation based on the distribution of jumps which the system undergoes in time tau. Okay, and he's not assumed very much about what this distribution is. He says if you know the distribution, you can calculate the diffusion constant exactly. Okay, and in fact in an experiment you can measure that distribution. You just look at it and see what happens. And so this theory is wonderful. It does contain a hidden assumption, which is that this function here, the distribution of the jumps you make, how far you jump in each time tau, depends only on delta and not on the past history. It's a Markov process. It doesn't depend upon, what happened 3 minutes ago, what happened 10 steps ago. It only depends upon what's happening now. It's a completely. It has no history. Doesn't know about history. So there's Perrin again. Let's look at diffusion. So let's look at Perrin's data. Okay. So Perrin's looking down a microscope at these particles moving around, and so his experiment's in 3D. He's got a drop of water which is in 3D, but he only sees a 2D cross section in a microscope, of course. Okay. So he took 365 paths. And he translated them so they all started at common origin. So he translated them, on when he's drawing the piece of paper, he says, oh, that one started there, that's my origin. Okay. And he just draws the dots where they got to. Okay. And he draws them out for different radii, rho. This is rho. Okay. Now, already when Perrin was doing the experiment, they knew how to solve the diffusion equation, and we know how to solve it as well for particular cases. And if we have a 3D diffusion with a particle starting at the origin, we have n particles starting at the origin. The total number of particles is conserved, which is the integration of density, and the solution in 3D is this one. Okay. Now, you can also apply it to one particle and interpret n as the probability density if you wanted to. Okay. So the only complication for Perrin's experiment is he has to go from 3D down to a 2D projection. And so we're going to let rho be the coordinate in the plane of the page. That's the plane of the microscope, but that's what he can see. And he drew rings of radius rho and width d rho. So here's these little rings here, which we've seen before. Okay. The distribution within those rings, we just need to integrate over our solution, which is, where's the solution? This is our solution. Plug it in. Figure out what r is in terms of z and rho. So we're going from r, which is sort of 3D sort of coordinates, 3D spherical polars, to rho and z, and the angular coordinate doesn't matter because it's sort of just, it's just this 2 pi business that's integrated over. And so here's the volume element in 3D for cylindrical coordinates, 2 pi, well, it's d phi, rho, dz, okay? And then he's calculated here the distance in spherical polars, converting to cylindrical polars, which would be this. That's the distance, it's Pythagoras. And this predicts how many particles he should see in a given ring. And you get an answer which looks like that. And in his experiment, psi is square root of 4 dt, and he finds for his particular times and size of diffusion, he finds xi is 7.16 micrometers. Okay, so that's his conversion from 2D to 3D. And there is his experimental data and the theory. And they both agree reasonably well. Okay, you can tell it's a bit of a sort of second year lab experiment. You've got some problems here, but that's what an experiment's like. If you've had all the points exactly in a line, people might be a bit suspicious. Okay, so what are the key points here? As I tried to emphasize at the start, the result is not sensitive to the exact form of the jumping probability, provided you can find this limit. This limit doesn't exist, and for some systems, this limit won't exist. There are certain kinds of weird random walks, Levi random walks, where you can't necessarily find that limit because it's not just the normalization, it's got this horrible delta squared thing which might make things blow up. But provided that limit exists for your random walk, we found the diffusion constant. And the other thing that's important here is, which will be emphasized later on, or maybe earlier on, I'm not sure, where we've done a great many random steps. Because of these random steps and they're not sort of related to each other, the distribution is Gaussian. Okay, this is a very general result. The central limit theorem. Everything lies on a bell curve. To a first approximation, that's true. Okay, so that's the other thing that's important here. Distribution is Gaussian. So, Perrin won the Nobel Prize for this in 1926 for his work on the discontinuous structure of matter, and especially for his discovery of sedimentation equilibrium. We would probably emphasize different aspects of his work these days rather than sedimentation equilibrium. But this is in some sense a perfect Nobel Prize because it's one bloke, one microscope, and one drop of water, and with some dirt in it basically. You can't get more fundamental than that. And it's, in my view, it's also the perfect prize because it doesn't involve building a telescope the size of Texas or a particle the size of Switzerland. It's about the real world. It's about stuff people are going to see. If you have to work really, really hard and build an enormous piece of apparatus to do your experiment, the problem is that means no one else is going to see it because they have to do exactly the same thing. Okay, whereas if you do your experiment with very small scale apparatus, it's probably important. Okay, so that's Perrin's prize, one of the best Nobel Prizes ever. Now, let's look at further work of Einstein here on what's called the Fluctuation-Dissipation Theorem. Okay, so it's Einstein again. I'm afraid Einstein is all over bits of modern physics, and it can't be helped. Okay, it's a very non-linear kind of subject. Some people contribute a lot. Okay, so we know the density gradient. If we have a density gradient, so more particles here than here, you get a current, which we've done before. There's a particle current which is proportional to the negative of the density gradient, and the proportionality constant is the diffusion constant. Okay, so we get a current flowing that way. But we can also get a current, of course, merely by having a potential or some forces acting on our particles. So if I have some particles here, and I put a, say, electric field like this, or a gravitational field, they will start moving, and that will induce a current of particles. Okay, not a current of charges, but a current of particles. So if you have them falling under gravity, you'll get a current due to gravity, not due to any density gradient. Okay, and so the external force is given by this. Okay, the negative gradient of the potential. If you have a viscous medium, like honey or oil, or even water, the particles will eventually reach a terminal drift velocity, proportional to the applied force. So you'll find eventually, if you wait long enough, if you apply a force, the particles, say, falling under gravity, will reach some terminal velocity u, often fairly quickly, and mu here is called the mobility, not to be confused with the chemical potential, which has also got the symbol mu. Okay, so for particles moving in a viscous medium, we know that the velocity, in the long term at least, will be equal to some constant times the force. Okay, so this drift causes a current density, which is the number of particles times the velocity, and that in turn might cause a concentration gradient. So if we have both external force and diffusion happening, then ultimately in equilibrium, if you reach an equilibrium situation, they must balance. So this J here must be balanced by the J due to the current drift, okay, due to the potential. All right. So, and we can put these two equations together with our formula for J, for diffusion, and for the particle current drift, particle drift. Those two things together, and that must be 0. Okay, so we get that equation there. Okay. However, we also know something from Mr. Boltzmann, and Mr. Boltzmann gives us the following formula for what the particle density must be as a function of position if you have a potential. So in equilibrium, we know this must be true. Vladimir has emphasized that to you many times. Okay, so let's put that together with that, and what we find out is we can plug that into there, and we get this, and then that wonderfully gives us a formula for the diffusion constant. Okay, and that formula for the diffusion constant, because these things cancel out, we can factorize it. It gives us a formula for the diffusion constant in terms of the temperature and the response of the particle to an external force. So remember, the diffusion constant is sort of telling you how much it walks randomly, and this mobility is telling you how much the particle responds to an external force, and this is the temperature, okay, which of course has something to do with the randomness as well. So this result is due to Albert Einstein, and it tells us how much if the particle is more mobile, the diffusion constant is higher. If the temperature is higher, the diffusion constant is also higher. So it makes perfect sense, but no one understood this before Einstein gave us the result. Okay, so how can we use this result? Well, there are 3 constants which were Pauli known in 1900. Okay, Avogadro's number, electric charge, and Boltzmann's constant. Perrin measured Avogadro's number using his experiment and got out these other 2 as a bonus, basically. So to get Avogadro's number, what we do is we start with Stokes' drag. So this is Stokes' drag, and the drag on the sphere, 6 pi eta, the viscosity in other words, times the radius times the velocity of the sphere. So that means the mobility, which is the inverse of the drag, divided by u, is given by that. Okay, that's our drag. Okay. So Wang has apparently made a mistake there. Okay, so we have this equation. This is our current equation. So therefore, from Einstein, we know this. That's our diffusion equation. kBt times the mobility, and kb is equal to r on Na, and so Na is equal to this. And basically, Perrin can measure all those things here. Okay, he measured D, in fact, in this case. And he got an Na, which is, not too bad from the modern value, not too far from it. Okay, so Perrin measured Avogadro's number. All right, so now we start leaving what you might call physics proper, and we're going into financial areas, financial mathematics. There's a whole area which some people call econophysics, which is not really physics at all, it's economics, but it applies the methods of statistical physics to economic systems, financial systems, and some of you may well end up working in these areas because because they pay well, I think, is part of the reason. Okay, so here's the Paris Bourse, the Paris Stock Exchange. And the reason why we're looking at the Paris Stock Exchange is because one of the great founders of this area of study was Louis Bachelier, who was a Frenchman and an exact contemporary of Perrin. So Perrin was born then and died then, and so did Bachelier. Okay. Now, Bachelier derived the diffusion equation from random walks in 1900, 6 years before Einstein. Okay, and other people have derived things as well. Lord Rayleigh did some work on adding up random sounds and similar kind of things. And Louis Bachelier is in some ways a typical academic. He survived on temporary positions until 1927, when he got an academic job, a permanent job, at the age of 57 in Besançon, which is it's in eastern France, in Alsace, really, or quite close to Alsace. And then he retired 10 years later. Okay, this is why a lot of people don't go into academia, because you don't get a proper job until you're a very advanced age. Okay, so that's the history of Mr. Bachelier. Let's look at the stock price. So the stock price on the stock market is called P of T. It can't possibly undergo a random walk because it has to be positive. You can't have a stock price. Here's the price, stock price P of T. Here's the axis. It can't. It can do this, but it's not allowed to do that. It can't go negative. That's not possible. So what people do is they look at the log of the stock price. Now, of course, the log of the stock price can be negative, and the assumption is that the Brownian model of stock prices, S of t, is assumed to be stochastic with a Gaussian distribution which has a drift and a width which increases as root t. So this is the distribution for the log of the stock price, and it depends upon t. So it's probabilistic. We're not going to give you the log of the stock price. This model does not predict it. What it does is it tries to predict the distribution, and S naught here is S, the log of the stock price at t equals naught. So that's that thing. This is the drift rate. Theta is the drift rate, and sigma here is the volatility, which has dimensions of t to the minus a half, and it's commonly taken as a measure of the risk. Okay, so there's a couple of things you have to know here. You have to know, or at least be able to measure somehow, the initial price, which that's pretty easy, the drift rate, which is a bit harder, and how much fatter it's getting all the time. This is the width of the distribution here, sigma. Okay. So let's look at some data. This is the S&P 500 for 1 day from 2003 to 2006, and we're going to plot of the distribution of log of P2 and P1, where P1's the price and P2 is the next day's price. And this thing will predict it because we can go forward in time 1 day if we want to. Let's compare those two. Okay, and we're trying to fit a Gaussian model to this, and we see, well, it's sort of okay, except these tails are not quite right. The tails are fatter than Gaussian, which probably tells you that the system is non-Markovian, that people remember what it was yesterday and what it was the day before yesterday and the day before that. Okay, and so people who deal in stocks and buy and sell stocks are not complete idiots. They look at the past history, so that's part of the reason why this is not quite as we might hope. And here's some more data here. This is for some dietary system, Nutrisystem, which is a weight loss dieting company. And if you read Wikipedia, it says, as of 2014, evidence was lacking that Nutrisystem produces help with long-term weight loss. This doesn't seem to prevent the company making money, however, so you can take what Wikipedia says with a grain of salt. Okay, so here is the stock price. There's the price, various years, and it's obviously going up, all right, all the time, which is a good thing if you have investments in it. And if we look at the weekly change in the stock price, remember this distribution here, we'll go way back. It tells us what it should look like as a function of time, and we can change the time. Okay, so if we look at the weekly change, delta S for the log of the stock price for various years, it should be a random walk with drift. That's the idea. Now it does fluctuate randomly. You can see it's going all over the place. and there are more points above than below the line. So there's more points up here than below, and so it does show some drift. Okay. But if we look at the variance, look at the data taken over the past 10 days and plot that, okay, the variance shows a constant band. So the variance is here sort of very more or less constant. But there are periodic spikes, like this, okay? And this Brownian model really can't describe what happens when the market does large movements. It's not a good model. Now, of course, you can't expect that it would be, because if this simple formula controlled the stock market, then it'd be very, very easy to analyze, and of course that doesn't work. But it works reasonably well given the extreme simplicity of the model. Now, in financial markets, people have much more sophisticated models, but we're not going to discuss those, in part because I don't know about them. Okay, so that's the end of this lecture.